Hi, this is Liz, and we're going to talk about binary search trees. The format is a little different this time. I have adapted some slides from Aaron Williams. He guest lectured on this topic for my discrete math class last year. So thank you, Aaron, for stepping in that time and for letting me adapt your slides for this lecture. All right. So if we were searching through a dictionary, and we know that uh, things are arranged in alphabetical order, but maybe we have some book that we don't know too much about, like say the Dictionary of Newfoundland English. So we might not know like what the distribution of different letters are, and how long it might take to find a word. So if you're just going in blind without knowing much besides that alphabetical order exists, and you wanted to sort of program something like a computer to search for a word, how would you do it? Like, what is the set of steps or the algorithm that you would give that computer to find a word? And how many flips would it take? So take a moment and think about if you were trying to describe a set of steps to find a word in an ordered dictionary, what would you do? All right, so one possibility is that you could sort of stick your finger in the middle of the book and look there and see if your word is before or after that middle word alphabetically. So that would be one option, and then you could just repeat that process. So you look at the midpoint, and if your word is after that point, you go to the upper half of what you've made so far, and then you could repeat that again, find the midpoint of the upper half, and if your word's below that, you would go to sort of the middle of that, the 1/2 to 3/4 part of the book, and so on. So how long would that take? If there are n pages, how much time does this take? Well, we're dividing something in half, and then dividing something in half again, and then dividing something in half again. How long does it take to get down to 1? Well, it takes log base 2 of n to get down to 1. So if we divided something in half once, we'd be down to n over 2 to the 1. Twice, we'd be down to n over 2 to the 2, and n over 4. 3 times, we'd be down to n over 8, and so on. And so if we divide in half, and notice that the log base 2 of 8 is 3, the log base 2 of 4 is 2, this is 1. So if we have divided k times, where k is equal to log base 2 of n, then that's the same as dividing n by 2 to the log base 2 of n. Remember that 2 to a power and log base 2 of something are inverse functions. They cancel each other out. So 2 to the log base 2 of n is n. And so dividing by that value is n divided by n. So if you repeatedly divide n objects in half log base 2 of n times, you will get down to one object after doing those divisions. Just a little bit more about log base 2 of n. So we discussed that a lot in our own course. So how many times in a row can we divide an integer n by 2 until reaching 1? Roughly log base 2 of n times, or big O of log base 2 of n times. A common goal in computer science is to reduce factors of n to factors of log base 2, because log base 2 of n is so much smaller than n. So here are some examples of algorithms and how long they take in big O notation. And we use log base 2 of n so often in computer science that we often denote it by just log of n or lg of n. We sort of forget about the base. We also saw when we looked at order of algorithms in our course that up to big O notation, log base b any base is big O of log base 2 and vice versa. So recall how much smaller is log of n than big O of n. Well, we worked with that as well in class. So remember, for example, that log base 2 of a million is approximately 20. Um, so log of n is much, 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 much smaller than n. So if we can reduce a factor from n to log base 2 of n, that is excellent. All right, let's get back to the question we were thinking about before. We want to look up a word in this Newfoundland English dictionary. And how long should it take? Well, if we're looking at, say, the Kindle edition has about 50,000 locations. If we take, and the actual book itself has about 847 pages. So we can take log base 2 of 847. Well, that's a little bit less than 10. So if we were doing an actual book and using this algorithm, it should take 10 flips of starting in the middle, dividing in half, to get down to the page you want. And similarly, if we were looking at the Kindle edition, which has about 50,000 locations, log base 2 of that value is approximately 16. So it should take 16 or fewer looks with in Kindle if we were doing that same kind of algorithm. So how about if we wanted to search for the word Teuton in the Newfoundland English Dictionary? Well, we would start by taking the midpoint of all those values in the Kindle locations, and that midpoint is, okay, Northern Dancers. Well, Teuton comes after Northern, so we would look in the latter half. So now we're in the second half of our book, and now we're dividing that second half in half, and we get Tatter. Okay, Tatter is before Teuton alphabetically. Now we can divide in half again, and we're looking at the second half, the latter half of that. And okay, that's kind of funny. We got these words that are not in alphabetical order. Well, some books have like a front matter and a back matter or an appendix, so it looks like we might be in the appendix of this book. So maybe we went too far. So it was too big, now we have to go in the lower half of that. And if we go in the lower half of that, okay, we're at Whittle. That's too big as well. We're going to go in the lower half of that. And now we're at Truckman. That is too big as well. We're going in the lower half of that. And Tom, it's pretty close, but a little bit smaller than Teuton. So we would go in the upper half of this. And let's see. So wow, we are there. There is Teuton, or also spelled in different ways, and it tells us what a Teuton is. It's a flapjack or kind of cake made with bread dough. And Erin and I actually did have some Teutons when we were up in Newfoundland, so it's a pretty cool part of northeastern Canada with a lot of its own dialect, obviously, enough to have a huge dictionary. But that's a Teuton, and they are very hard. So it's not a soft dough, it's something you could bang on the table. So what just happened? We had this summary of our guesses, and at first we said, okay, the first thing was too small, too big, and each time, if it was too small, we looked in the lower half of what we had just divided ahead of time, the lower half of what we just divided ahead of time. If it was too big, we looked in the upper half of what we had just divided ahead of time. So we had said that we could do this in less than or equal to 16 guesses. It happened that we did this in far fewer than 16 guesses. We happened to be lucky on that last guess. It just so happened that we didn't have to go all the way down to a length of 1. We only had to go down to a length of 387 to get to Teuton this time. All right, we've already done this. We've already discussed log base 2 of n, but it's a very important topic and something I really want you to leave this class knowing. So feel free to linger on this page if you'd like. We now want to talk about binary search trees. So what we were just doing with that Newfoundland dictionary was a binary search algorithm that at each point we compare a value t that we are searching for, the target, or Teuton in this case, to the value m in the middle of the array. If t is less than m, then m can be located in the must be located in the first half of the array. If t is equal to m, like when we got to page 3, when we got to our page and we found Tootin, then we've been found and we can finish. And if t is greater than m, then t can only be located in the second half of the array. We're searching for t. If we were, for example, searching for -1 in this sorted array, and it's an array of values, and it's sorted, meaning it's already in numerical order in this case. So we're searching for -1 in this sorted array. So we start at the middle value. -1 is less than 3, so we look at the lower half. Now we look at the middle value of this, -2. -1 is larger than -2, so we look at the upper half of this. All right, now we're looking at the middle value of this, which is 1, and -1 is less than it, so we go to the lower half of that and look at the middle value. There's only one value left, and that wasn't -1. So we didn't actually find -1. What we observed was that the algorithm has observed that -1 is not even in that array at all. So you want your algorithm both to be able to find a value if it's in there, and to come back and say, hey, that value was not in my list of data at all. So this binary search algorithm can do that, and the algorithm takes log base 2 of n time, as opposed to linear search, which takes big O of n time. All right, so why do we need binary search trees? Just big picture, remember that big O of f of n is basically the worst case amount of time a function f of n takes to process n data points. So our goal is always to make f of n as small as possible for regularly used functions. And so we saw that a sorted array can find an object in log of n time, but the issue is that if we also want to insert or delete objects, then this will take big O of n time. So if we have an array, a list of values sorted in order, then anytime that we want to add a value or delete a value, that costs a lot of time. So if you're dealing with a static set of data that you are never going to change, then using a sorted array is great. If you're never going to change that data, if you're never going to insert or delete data values, then using a sorted array is just as good as using a binary search tree. However, if you ever do want to insert new data or delete old data, then an array is not what you want to use. You'd instead want to use a balanced binary search tree, which is what we'll be talking about. And a binary search tree, if it's balanced, can find, insert, and delete data points in log n time. And remember, log n time is so much smaller than n, and so that is really of a great benefit. It also compares binary search trees to linked lists, and it can be either singly linked lists like this or doubly linked lists. But we see that linked lists also take big O of n to find and to delete items, as compared to binary search trees, which take log n time for all three operations. If you'd like more details on this and why it is true, I'm also putting an extra video that I did not make in the comments of this video. Okay, so as we saw, we looked before at sorted arrays and finding a data value or determining a value what didn't exist in a particular array. So how does that translate to a binary search tree? Well, we are basically repeatedly taking the median or the middleist value down to the next available level, and then repeating the procedure for the left subarray and the right subarray. So first we have the middle value of 15. That's the mean value. The median value out of those 9 values is the 5th value. And so that's going to be the root of our binary tree. Now everything down here is going to be on the left side, and everything up here is going to be on the right side. So we again look at the middle value out of what is left, and 7 is our middle value. Actually, 0 or 7 would equivalently work. We can just arbitrarily always take the larger one, but it doesn't matter. So here's our value 7, and our value on this side, the middle of these 4 numbers. Again, we could use either of those two, but we're going to use this value. Then we can do our next level of our tree. And in our next level of our tree, we've got down here, we've got 0 and -3 still to fit in. And up here, we've still got 10 and 15 to fit in. So we're taking the middlest value that's left over. Between these two, -3 and 0, it really doesn't matter which one we pick. We'll take 0. Between these two, doesn't matter, we'll take 10. And same thing is happening over on the right side. And now there's only one value remaining. It's smaller than 0, so it's going as a left child. And here as well, there was only one value remaining. It's smaller than 44, so it's going as a left child. So this creates tree-like structures. And we talked about trees in our graph theory so far. So let's review some different types of trees. Remember that a tree is a connected acyclic graph. That is, a tree is connected and has no cycles. A leaf is a vertex of degree 1. We didn't talk about that. And the other vertices are called internal vertices. So this is a tree with 4 leaves, 1, 2, 3, 4, and 4 internal vertices, 1, 2, 3, 4. We saw that a tree on n vertices always has n-1 edges, and it's also true that there is a unique path between any 2 vertices within a tree. A rooted tree is a tree that has a specified node root node r, and the level of a node is its distance to r, and the height of a tree is its maximum distance. This level is level 1, this level is level 2, and so this is a tree of height 2. Every edge joins a parent to a child, where the parent is closer to R. So this is the child of this node, and this is the parent of that node. This is the parent of this node, but the child of that node. So these nodes have no children or no descendants. And we draw the root R at the top, and each other node below R is based on its level. In general, there can be cardinal trees. A k-ary cardinal tree is a rooted tree where its children go from 1 up to k, and each specified child can be present or absent, and there can be at most one of each. So this would be, for example, a node in a 4-ary tree or a ternary tree, and it has a first, third, and fourth child, but it's okay that the second child is missing. This is a node in a binary search tree with both a left and a right child. Yes, they're called left and right children in a binary search tree because there are only 2, so we can distinguish easily between left and right, whereas we could not in a ternary tree, in a four-nary tree, for example. Binary search trees and heaps are both labeled binary trees, and they have a lot of special properties. So here's an example of a binary tree at this point with no labels. Note that each parent has at most 2 children, but the parent can have only a left child or, in theory, only a right child. And the pointers are pointing from parent to child. A binary search tree is a binary tree with values at each node that satisfy these following conditions. So if x is the value of a node and y is a value in its left subtree, then x is greater than or equal to y. And if x is the value of a node and y is a value in its right subtree, then x is less than or equal to y. So in other words, here we have a node, and all values on its left subtree are less than or equal to x. All values in its right subtree must be greater than or equal to x. And so here's an example of a binary search tree. 1 is less than 3, great. Everything to the right of 3 should be larger than 3, so everything here is bigger than 3, or greater than or equal to 3. And everything in this left subtree should be less than or equal to 8. Everything in this entire right subtree must be greater than or equal to 8, and so on. So to make sure that you understand this definition of binary search tree properly, what I'd like you to think about is the following question. So recall that we defined a binary search tree to be one that fits these two conditions. If x is the value of a node and y is the value in one of its left subtrees, then x has to be greater than or equal to y. And if y is in the right subtree of x, then x is less than or equal to y. Okay, so that's the definition. The question is this definition below equivalent? So consider these two edge conditions for a binary tree with values in its nodes. If x is the value of a node and y is also a vertex, so computer scientists sometimes refer to vertices as nodes, but anyway, if x is the value of a node or a vertex and y is the value of its left child, then x is greater than or equal to y. If x is a value of a node and y is the value of its right child, then x is less than or equal to y. So basically the question is this definition equivalent to this definition? So if you make something that satisfies these properties, if you make a search tree, a labeled tree that satisfies these properties, will it necessarily be a binary search tree? Will it necessarily satisfy these properties? Here's a spoiler, the definitions are not equivalent. So try to provide a counterexample. Try to find a binary search tree that try to give a binary tree, not a binary search tree, but just a binary tree that satisfies these conditions, but does not satisfy these conditions, does not make, is not properly, it's not a proper binary search tree. So satisfies the edge conditions, but not the subtree conditions that define a binary search tree. So actually pause, take a moment and think about that. Try to make your counterexample as small as you can. So think about that. Dun, dun, dun. Okay. So here is one example where the edge conditions are met, but the subtree conditions defining a binary tree are not met. So here we've got 10, and then 5 is less than 10, so it goes to the left. So this is met. X equals 10 is the node, and y is the value of its left child, and x is greater than or equal to y. Great. Now, the edge condition here is still met. X equals 5 is the value of the node, and y is the value of its right child. So y is greater than or equal to x. So we see that the edge conditions here are both met for this binary tree. However, these conditions are not met. So we see that in this case, 20 is in the left subtree of 10, but 20 is not less than or equal to 10. So this is not a valid binary search tree. It is a binary tree, but it is not a binary search tree. So this is just enforcing this definition and what it means. So this is not a binary search tree. So take a look at your example and see if you are also able to construct such a counterexample. All right, so that is the end for this video, and we will continue talking about binary search trees with binary search tree operations and with different ways of going through a binary tree in the next video.